Chapter 0: The Illusion of Infallibility. When we look up at the night sky, we are often struck by a sense of order. The stars seem to follow their paths with extraordinary patience. The moon waxes and wanes. The planets return. And from the surface of our small world, the universe can seem like an immense equation slowly revealing itself. For centuries, we have relied on remarkable minds to translate that order into mathematics. Their names have become part of the architecture of science. Einstein, Galileo, Fermi, Eddington, Hoyle, Kelvin, Tesla. We remember them for the moments when they saw farther than almost anyone around them. But scientific history is not a straight road from ignorance to truth. It bends, it doubles back, and sometimes the people who understand nature most deeply are also the people who become most attached to a particular picture of how nature ought to behave. Tonight, we are going to explore those moments. Not failures of intelligence, and not simple stories of foolishness. Something more interesting. Moments when extraordinary scientists followed an idea too far. When a beautiful assumption became difficult to abandon. When incomplete information looked complete. When reputation gave an argument more weight than it deserved. And when the universe refused to fit inside a framework that had once seemed perfectly reasonable. These mistakes were not all alike. Some slowed progress. Some were corrected quickly. And a few were so intellectually productive that the questions they created became almost as important as the answers that eventually replaced them. That is one of the peculiar strengths of science. A theory does not have to survive forever to matter. Sometimes an incorrect model teaches people what to measure next. Sometimes an objection forces a theory to explain itself more clearly. Sometimes a stubborn disagreement exposes a hidden assumption that nobody had noticed before. And sometimes the most useful thing a brilliant person can do is be wrong in an interesting way. There is something reassuring in this. The great figures of science were not standing outside the human condition, looking directly at reality without distortion. They carried preferences, habits, intuitions, ambitions, and limitations, just as everyone does. They wanted nature to make sense. They wanted its rules to be coherent. And sometimes they wanted those rules to resemble the world they already knew. But nature is under no obligation to protect our intuitions. The universe can expand when we expect stillness. A nucleus can break when we expect it merely to grow heavier. A star can reach a limit beyond which familiar matter can no longer support it. Two quantum systems can remain correlated across distances in ways that challenge ordinary ideas of separateness. And the Earth beneath our feet can be billions of years older than an elegant equation first suggests. So tonight, there is no need to search for heroes or villains. Only people thinking at the edge of what was known. People building maps of territories no human being had visited before. Some of those maps were astonishingly accurate. Others contained beautiful mistakes. And as we move slowly through these stories, we may discover that the history of science is not weakened by those mistakes. It becomes more human because of them. Chapter 1: The Illusion of a Static Sky. For most of human history, the night sky offered an impression of permanence. Individual stars moved across the heavens each night, and the planets wandered slowly against them, but the cosmos as a whole seemed ancient and settled. At the beginning of the 20th century, even after physics had undergone enormous change, the idea of a universe that was broadly static still felt natural. Albert Einstein shared that expectation. In 1915, he completed the general theory of relativity, a new description of gravity in which matter and energy influence the geometry of space and time. It was an extraordinary achievement. But when Einstein began applying the theory to the universe as a whole, a difficulty appeared. A cosmos filled with matter was not naturally content to remain exactly as it was. The equations allowed change. Expansion, contraction, evolution. Einstein, however, was trying to construct a model of a universe that was static on the largest scales. So in 1917, he added a new term to his gravitational equations: the cosmological constant. With an appropriate value, it could help produce the static cosmic model he wanted. This is often described as Einstein forcing his mathematics to obey a philosophical prejudice. The real history is gentler than that. At the time, there was no established observational picture of an expanding universe. The Great Spiral Nebulae had not yet even been firmly recognized as distant galaxies beyond the Milky Way. Einstein was working with the universe astronomers thought they knew. But that universe was already beginning to change. In 1922, Alexander Friedmann showed that Einstein's equations admitted expanding and contracting cosmological solutions. A few years later, Georges Lemaître independently developed an expanding model, and in 1927 connected it with astronomical observations. Meanwhile, astronomers were measuring the strange spectra of distant spiral nebulae. Vesto Slipher had already found that many of them showed large redshifts. Then Edwin Hubble made crucial measurements of their distances and demonstrated that some of the fuzzy spiral objects in the sky were enormous stellar systems far beyond our own galaxy. In 1929, using his distance estimates together with radial velocities that came largely from Slipher's observations, Hubble published the famous relation between distance and recession velocity. The farther away a galaxy appeared to be, the faster it tended to recede. The old static picture was becoming increasingly difficult to maintain. There was another problem as well. Einstein's carefully balanced static universe was unstable. A small disturbance would cause the balance to fail. By 1931, Einstein had abandoned his original static model and turned toward an evolving universe. The cosmos had refused to remain still. But this story contains one final turn. For many years, the cosmological constant was treated as an unnecessary remnant of Einstein's early cosmology. Then, late in the 20th century, astronomers discovered that the expansion of the universe is accelerating. And a cosmological constant, no longer used to hold the universe static, but associated with the energy of empty space in the standard cosmological model, returned to the equations. The term Einstein once introduced for one reason had found an entirely different role. His mistake then was not simply adding the cosmological constant. It was believing too soon that the universe ought to remain unchanged. And perhaps that is the quieter lesson. Sometimes even the right piece of mathematics can enter a theory for the wrong reason. The universe keeps the part it needs and lets the rest fall away. Chapter 2: The Invisible Fracture. There is something strange about studying the atomic nucleus. We cannot reach inside it with our hands. We cannot watch its components move with an ordinary microscope. Instead, physicists disturb it and study what comes back. A particle enters. Radiation emerges. A detector clicks. And from those traces, a hidden event must be reconstructed. In the early 1930s, Enrico Fermi became one of the great masters of this indirect art. The neutron had recently been discovered, and Fermi immediately understood that it could become an unusually effective probe of the nucleus. Because a neutron carries no electric charge, it can approach a positively charged nucleus without facing the same electrical repulsion that obstructs charged particles. Fermi and his colleagues in Rome began bombarding element after element with neutrons. Again and again, they produced new radioactive substances. Then they reached uranium. Uranium was element 92, the heaviest element known in nature. When the team exposed it to neutrons, they detected several unfamiliar radioactive products. The natural interpretation seemed exciting. Perhaps a uranium nucleus had absorbed a neutron, and after subsequent transformations, produced elements beyond uranium. New entries in the periodic table. Elements 93 and perhaps 94. It was an understandable conclusion. Most known nuclear reactions involved relatively modest rearrangements. A nucleus might capture something, emit something, or transform into a neighboring element. The idea that a heavy nucleus might break into two large pieces was much harder to imagine. But one scientist did imagine it. In 1934, the German chemist Ida Noddack published a criticism of the transuranium interpretation. Before declaring a completely new element, she argued, researchers should make sure the mysterious products were not actually known elements much farther down the periodic table. And then she suggested something remarkable. Perhaps after being struck by a neutron, a heavy nucleus could break into several large fragments. The suggestion was close to what we now call nuclear fission. But neither Fermi's group nor most other nuclear physicists pursued it. There was no convincing theoretical framework for such a process, and the idea seemed too extreme. 4 years passed. Then, at the end of 1938, Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and found something they had enormous difficulty explaining. One of the products behaved chemically like barium, an element far lighter than uranium. Soon afterward, Lise Meitner and her nephew Otto Frisch supplied the physical interpretation. The uranium nucleus had divided. Frisch gave the process its familiar name: fission. Looking backward, it became clear that some of the mysterious activity produced in the earlier uranium experiments had probably included fission products as well. Fermi's laboratory had come remarkably close to the phenomenon without understanding what it was seeing. His 1938 Nobel Prize did not recognize the discovery of fission. It honored his work on neutron-induced radioactivity and the effectiveness of slow neutrons. The missed discovery belonged to a wider scientific blind spot. Fermi was not alone. Many of the finest nuclear physicists in Europe struggled to imagine that a nucleus could divide in this way. That may be what makes the episode so revealing. Expectation is useful. Without expectation, data are only scattered signals. But expectation can also become a filter. We notice what fits the pattern already in our minds. And sometimes the most important signal is the one that does not belong there. A strange chemical result. An inconvenient measurement. A possibility that seems much too radical. Sometimes the door to a new world is not locked. It simply does not look like a door. Chapter 3: The Weight of Authority. A star spends much of its life in balance. Gravity pulls inward. Pressure pushes outward. And for millions or billions of years, those opposing tendencies can remain in a kind of luminous equilibrium. But stars eventually change. Their fuel is altered. Their cores contract. And the question of what remains after a star can no longer support itself became one of the great problems of 20th century astrophysics. In the early 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar began thinking about one possible stellar remnant: the white dwarf. White dwarfs are extraordinarily dense. The matter inside them is supported not by ordinary thermal pressure alone, but by a quantum mechanical effect known as electron degeneracy pressure. On a long voyage from India to England in 1930, Chandrasekhar began combining this quantum physics with Einstein's special relativity. And he encountered a limit. As the mass of a white dwarf increases, its electrons must move faster and faster. Once relativistic effects become important, degeneracy pressure does not strengthen rapidly enough to support an arbitrarily massive white dwarf. There must be a maximum mass. In modern calculations, it is roughly 1.4 times the mass of the Sun, depending somewhat on composition and other details. Above that limit, a stable white dwarf cannot exist. This was a profound result, but it did not yet provide a complete description of what would happen next. Chandrasekhar had found a boundary. Beyond it lay physics that was still being developed. One of the most influential astrophysicists in the world was deeply unhappy with the result. Sir Arthur Eddington had made fundamental contributions to the physics of stars and had played a famous role in the 1919 eclipse expeditions that helped bring Einstein's general relativity to international attention. Eddington understood stellar structure as few people did, and he distrusted Chandrasekhar's conclusion. At a meeting of the Royal Astronomical Society in January 1935, Chandrasekhar presented his work. Eddington spoke immediately afterward and attacked the relativistic treatment behind the limiting mass. He argued, in effect, that nature must contain some way of preventing such an absurd stellar collapse. For Chandrasekhar, the episode was deeply discouraging. Eddington was not merely another scientist in the room. He was one of the great authorities of the field. And authority changes the atmosphere around an argument. An objection from an unknown researcher and an objection from Arthur Eddington did not carry the same social weight. Still, the story was not as simple as one powerful man silencing an entire scientific community. The theoretical landscape continued to change. The neutron had only recently been discovered. The idea of neutron stars was emerging. And later work on gravitational collapse would reveal still more extreme possibilities. Eventually, astrophysics learned that stars above the white dwarf limit can follow different paths depending on their mass and evolution. Some leave neutron stars. Others can collapse far enough to form black holes. Chandrasekhar himself would go on to study many areas of astrophysics, including black holes much later in his career. And in 1983, he received the Nobel Prize for his theoretical studies of stellar structure and evolution. The limit he discovered as a young man became one of the foundations of modern astrophysics. Eddington's mistake was not simply that an older scientist disagreed with a younger one. Disagreement is how science works. The more subtle danger was that an intuition backed by enormous prestige could feel almost like a law of nature. Even a correct calculation can sound impossible when it points beyond everything a field is ready to imagine. And sometimes a young scientist does not see the final destination. He only sees that the old road must end. That can be enough. Chapter 4: The Sound of the Beginning. There is a natural temptation to ask whether the universe has always existed. The question feels almost older than science itself. If everything around us has a history, perhaps the cosmos has one too. Or perhaps the universe simply is. No first moment. No final boundary. Just an eternal background against which stars and galaxies slowly rearrange themselves. Fred Hoyle was drawn to the second possibility. Hoyle was one of the most creative astrophysicists of the 20th century and one of the key architects of our understanding of how stars manufacture chemical elements. He helped reveal that the carbon, oxygen, and many heavier elements found throughout the universe could be built through nuclear processes inside stars. Yet when it came to cosmology, Hoyle preferred a universe without a beginning. In 1948, Hoyle, Hermann Bondi, and Thomas Gold developed versions of what became known as the steady-state theory. They accepted that the universe was expanding, but they proposed something remarkable. As galaxies moved farther apart, tiny amounts of new matter would continuously appear, allowing the average large-scale universe to remain essentially the same through time. The universe could expand without becoming fundamentally different. No unique beginning was required. The following year, Hoyle described competing cosmological models during a BBC radio broadcast. He referred to theories in which the matter of the universe had been created in a single Big Bang in the distant past. The phrase survived. There is a popular story that Hoyle invented it as an insult. The evidence is much less certain. Hoyle strongly disliked cosmologies with a beginning, but he later said that on radio he was searching for a vivid verbal image. Whatever his intention, two short words eventually became the name of the theory that defeated his own. But the modern Big Bang should not be imagined as an ordinary explosion. There was no central point in pre-existing empty space from which galaxies were thrown outward like fragments from a bomb. The theory describes an early universe that was extraordinarily hot and dense, and a cosmos whose scale has changed with time. The space itself expands. During the 1950s and early 1960s, astronomers searched for ways to distinguish this evolutionary universe from steady-state models. The differences mattered. If the universe changed with cosmic time, distant regions should not always resemble nearby ones. If it remained in a steady state, the statistics of the distant universe should tell a different story. Gradually, the observations became uncomfortable for Hoyle's model. And then came a faint microwave signal. In 1964, Arno Penzias and Robert Wilson were working with a sensitive antenna at Bell Laboratories when they encountered an unwanted background noise that seemed to arrive from every direction. The following year, its cosmological significance became clear. This was the cosmic microwave background, relic radiation from a time when the universe was much hotter and denser than it is now. For steady-state cosmology, it was a severe and ultimately devastating problem. For hot Big Bang models, it was exactly the kind of ancient radiation that an evolving early universe could leave behind. The discovery did not tell physicists everything about the ultimate origin of the universe. It did not prove that cosmology had reached an absolute first instant. But it transformed the debate. The cosmos had a thermal history. The distant past was physically different from the present. Hoyle continued to explore alternative cosmologies for the rest of his life. That persistence can look stubborn in retrospect. But steady-state theory had also served science well. It was clear enough to be tested. It made predictions. And because it made predictions, nature could answer. That is an important kind of failure. A vague idea can survive indefinitely. A precise idea risks being killed by evidence. Hoyle's universe did not survive. But the contest helped make cosmology a more observational science. And the man who resisted the hot early universe gave it the name by which almost everyone now knows it. Chapter 5: The Clock in the Stone. The Earth carries time in ways that human intuition does not easily grasp. A coastline retreats grain by grain. A river deepens a valley. Sediments settle in layers. Mountains rise and erode. And over spans of time far longer than any human life, continents themselves move. By the 19th century, geologists had become increasingly convinced that the history recorded in rocks required an ancient Earth. Charles Darwin's theory of evolution also seemed to demand enormous stretches of time. Then physics appeared to disagree. William Thomson, later Lord Kelvin, was one of the greatest physicists of his century. He had made fundamental contributions to thermodynamics and understood heat flow with extraordinary mathematical power. Kelvin approached the age of the Earth as a problem in cooling. Suppose the young Earth had once been extremely hot, perhaps largely molten. Over time, it would lose heat through its surface. If you knew the present temperature gradient inside the crust and understood how efficiently rock conducted heat, perhaps you could calculate how much time had passed. Kelvin did exactly that. His estimates changed over the decades as he altered assumptions and improved the calculation. Earlier ranges were broad. By the end of the 19th century, he favored an age on the order of a few tens of millions of years, somewhere near 20 to 40 million. That was far longer than human history. But for many geologists and evolutionary biologists, it was alarmingly short. Kelvin had something they did not: a quantitative physical argument. And numbers carry authority. Geologists could point to landscapes, sedimentary sequences, and fossils that seemed to require deep time. But Kelvin could answer with equations. The disagreement became one of the great scientific tensions of the period. The standard retelling often gives the story a simple ending. Kelvin did not know about radioactivity. Radioactive elements inside the Earth generate heat. Therefore, Kelvin's planet cooled more slowly than he thought. That is part of the story, but it is not the whole of it. The deeper flaw was in Kelvin's model of how heat moved through the Earth. He treated the planet largely as a body cooling by conduction. But the Earth's mantle can transport enormous amounts of heat through very slow convection. Hotter material rises. Cooler material sinks. Over geological time, the interior is not merely a motionless solid through which heat diffuses. Remarkably, one of Kelvin's former assistants, John Perry, pointed out this problem in the 1890s, before radioactivity was discovered. If the deep Earth could convect efficiently, while a comparatively thin outer layer conducted heat, Kelvin's thermal argument could allow a much older planet. Then radioactivity opened another door. It provided internal heat. And even more importantly for determining geological ages, radioactive decay eventually gave scientists a new clock. Atoms themselves could record time. During the 20th century, radiometric dating and a much deeper understanding of Earth's interior established an age of roughly 4.5 billion years. Kelvin's few tens of millions had been far too small. Yet his mathematics had not simply been careless. The mistake lived in the model surrounding the mathematics. He had described a planet simpler than the real Earth. That is a recurring danger in science. An equation can be solved perfectly and still produce the wrong world. The assumptions enter quietly. They may seem harmless. They may even seem obvious. And because they are hidden underneath elegant mathematics, they can be harder to question than the mathematics itself. The rocks had been keeping time all along. Humanity simply needed a better clock. Chapter 6: The Roll of the Dice. There is comfort in a predictable universe. Release a stone and it falls. Push a pendulum and its motion follows equations. Know the starting conditions well enough, and classical physics seems to promise that the future can be calculated. Albert Einstein helped transform that classical world. But he never became comfortable with one of the revolutions that followed. Quantum mechanics. At atomic scales, the theory does not generally predict a single outcome for every individual event. It predicts probabilities. A radioactive atom has a probability of decaying. A particle prepared in a particular quantum state can yield different results when a measurement is made. The mathematical theory works with extraordinary precision. But what its probabilities mean about reality has been debated for more than a century. Einstein never doubted the spectacular empirical success of quantum mechanics. His concern was deeper. He doubted that the theory, as usually interpreted, was a complete description of physical reality. He disliked the idea that fundamental events were irreducibly random. And he was deeply troubled by what happened when quantum systems became entangled. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published one of the most famous thought experiments in physics. Imagine two systems that interact and then move far apart. Quantum mechanics can describe them with a shared state. Measure one system, and you can predict correlated results for the other, even when the two are widely separated. Einstein believed this created a serious problem. If an action performed here could not physically disturb something far away faster than light, then perhaps the distant system must already possess definite properties that the quantum description failed to include. In that case, quantum mechanics would be incomplete. Einstein hoped that beneath the probabilities there might be a deeper description. The argument did not disappear. It became more important. In 1964, physicist John Bell discovered a way to turn philosophical disagreement into an experimental question. A broad class of theories in which measurement results were determined by pre-existing local hidden variables would obey certain mathematical inequalities. Quantum mechanics predicted that those inequalities could be violated. Experiments became increasingly sophisticated. Again and again, the quantum predictions survived. The correlations found in nature are stronger than local hidden variable explanations of the Bell type can reproduce. But this does not mean that entangled particles send ordinary messages to one another faster than light. Quantum entanglement cannot be used as a controllable faster-than-light communication channel. The strangeness is subtler. Nature appears unwilling to fit simultaneously into all of the classical intuitions that Einstein hoped to preserve. So was Einstein simply wrong? not in the simple way this story is sometimes told. He did not expose an embarrassing flaw in quantum mechanics. But his objection forced physicists to ask what the theory was really claiming. The EPR argument helped inspire Bell. Bell inspired generations of experiments. And those experiments helped create the conceptual foundations for modern quantum information science. One of Einstein's strongest objections to quantum theory eventually helped reveal just how remarkable quantum theory really is. There is an irony in that. Sometimes resisting a theory does not stop progress. Sometimes the resistance becomes part of the progress. Einstein wanted a deeper layer of order beneath quantum probability. He never found the theory he hoped for. But the questions he refused to abandon became some of the most productive questions in modern physics. The dice remained. And because Einstein kept asking why they were there, we learned far more about how they fall. Chapter 7: The Rhythm of the Sea. The tides are among the most familiar motions on Earth. On many coastlines, the sea rises and falls in a rhythm close to twice each day. The timing shifts. The height changes. Harbors amplify the water. Some places experience very different patterns from others. Yet beneath all of that complexity lies a regular relationship between the oceans, the Earth, the Moon, and the Sun. In the early 17th century, that relationship was not understood. Galileo Galilei believed the tides might solve a different problem. He wanted physical evidence that the Earth moved. Through his telescope, Galileo had seen mountains on the Moon, satellites circling Jupiter, and phases of Venus that challenged older pictures of the heavens. He had become a committed defender of the Copernican idea that Earth was a planet moving around the Sunday. But astronomical evidence was one thing. Galileo wanted a physical effect here on Earth that could be explained by the planet's motion. He turned to the sea. Galileo imagined the oceans inside their basins, somewhat like water inside a moving vessel. Earth rotated once each day while also traveling around the sun. He reasoned that the combination of those motions would cause the speed of different parts of Earth's surface to change through the day. The oceans, unable to adjust instantly, would slosh back and forth. The tides, he believed, were the visible consequence. This explanation appealed strongly to Galileo because it was mechanical. Matter moved because other matter moved. No mysterious influence had to reach across empty space. Johannes Kepler proposed something very different. Kepler suspected that the Moon exerted an attractive influence on the Earth's oceans. He did not possess Newton's later theory of universal gravitation. But qualitatively, he had noticed the correct connection. Galileo rejected it. To him, the suggestion sounded too much like the hidden sympathies and occult influences that older natural philosophy often invoked without mechanical explanation. A distant moon somehow commanding the sea felt less scientific than water being accelerated by the motion of its container. In this case, Galileo's demand for a mechanical explanation led him away from the correct cause. Decades later, Newtonian gravitation provided the framework Galileo lacked. The Moon's gravity acts slightly differently on different parts of Earth. The Sun contributes as well. These differences produce tidal forces, while Earth's rotation, the shapes of ocean basins, coastlines, and other effects determine the complicated tides actually observed at particular places. Galileo's model could not account correctly for that behavior. His proposed proof of Earth's motion failed. But heliocentrism did not fail with it. This is what makes the episode valuable. Galileo is remembered as a champion of observation against inherited authority. And he was. Yet even a scientist famous for challenging assumptions could become trapped by an assumption of his own. He had decided what a respectable physical cause ought to look like. Kepler's invisible attraction did not fit. A century later, invisible gravitational interaction would become one of the central organizing principles of physics. The sea had been responding to the sky all along. Galileo had simply chosen the wrong conversation between them. Chapter 8: The Ghost in the Machine. At the end of the 19th century, electricity was reshaping the modern world. Generators grew larger. Motors became more practical. Cities began to glow after sunset. And among the engineers and inventors driving that transformation was Nikola Tesla. Tesla made major contributions to polyphase alternating current systems and developed an influential induction motor based on a rotating magnetic field. He experimented with high-frequency currents, transformers, and wireless transmission. His ability to imagine electrical machines was extraordinary. But the physics surrounding electricity was changing just as quickly as the technology. For much of the 19th century, physicists had assumed that light waves must travel through some medium. Sound moves through air. Water waves travel through water. So perhaps light also required something to wave through. That hypothetical medium became known as the luminiferous ether. By the time Tesla was developing his electrical systems, however, the ether was already becoming a serious theoretical problem. Experiments had failed to reveal the Earth's expected motion through it. And in 1905, Einstein's special theory of relativity showed that electromagnetic theory did not require a mechanical ether that defined an absolute state of rest. 10 years later, general relativity changed the picture again. Gravity could be described through the geometry of space-time. Mass and energy influence that geometry, and objects move through the resulting curved space-time. This was a very different universe from the mechanical one in which Tesla had formed many of his intuitions. Tesla did not accept the change. In interviews and public statements during the 1930s, he criticized Einstein's relativity and rejected the idea that space itself could possess curvature. To Tesla, space without matter was nothing. And nothing, he argued, could not bend. He continued to favor versions of an ether-like physical medium and looked for more mechanical explanations of gravitation and electromagnetic phenomena. By then, mainstream theoretical physics had moved elsewhere. Relativity had survived major observational tests. Quantum theory was developing rapidly. And Tesla's later cosmological ideas had little influence on the direction of fundamental physics. There is a temptation to make this part of his life tragic. The inventor of the future trapped inside the physics of the past. But perhaps there is a more useful way to understand it. Expertise has boundaries. A person can possess astonishing intuition in one domain and far less reliable intuition in another. The ability to design an electrical motor does not automatically confer authority over cosmology. The ability to revolutionize engineering does not guarantee that every physical theory will feel intuitive. And great success can sometimes make an old framework even harder to abandon. After all, that framework once worked. It helped produce real machines, real currents, real rotating fields, real inventions. Then the map changed. The deepest revolutions in science often demand exactly that kind of surrender. Not surrender to another person's reputation. Not surrender to fashion, but surrender to evidence when a familiar picture can no longer contain it. Einstein had to give up his static universe. Fermi's generation had to accept that a nucleus could split. Eddington's picture of stellar matter could not escape Chandrasekhar's limit. Steady-state cosmology had to face a universe with a thermal history. Kelvin's cooling Earth had to become a convecting, radioactive planet. Galileo's mechanical tides gave way to gravitational interaction. And classical intuitions about separateness were challenged by quantum entanglement. Tesla's ether belongs to the same long story. Not the story of foolish people being corrected by clever ones. The story of human beings building models, trusting them, testing them, and sometimes reluctantly learning when to let them go. That may be the quietest lesson of all. Science advances not because scientists are immune to error. It advances because no scientist, however brilliant, gets the final word. The universe keeps answering, and patiently, generation after generation, we learn to listen.